Today we are walking through the paper titled On the Geometry of On-Policy Distillation.
Start with the main question. What does this paper want to understand?
The paper studies OPD, a way to improve a reasoning language model by letting the student generate its own answers, then distilling teacher token distributions on those on-policy rollouts. The open question is not whether OPD can improve reasoning, but what kind of parameter update it creates inside the model.
So the focus is the shape of the update, not just the final benchmark score.
Exactly. Prior work had already separated SFT and LVR geometrically. SFT tends to rewrite many weights and loaded important range directions. LVR tends to be sparse and off principle. This paper asks where OPD sits in that spectrum, and whether its trajectory changes over training.
Before the results, what does on-policy distillation mean here?
In this setup, the student model samples the response tokens. Then the teacher provides token-level probability information on those same rollouts. So OPD keeps the on-policy sampling flavor of our LVR, but replaces a single sequence-level reward signal with denser teacher-student disagreement at the token level. The authors use Q and 3 family checkpoints and compare OPD against SFT and LVR. For the main Q and 3-8P comparison, OPD and LVR start from the same SFT anchor and use the same math domain prompt distribution, which makes the geometry comparison cleaner.
What tools do they use to measure that movement?
They use for diagnostics. First, bfloat 16, where sparsity asks how many weight entries visibly changed after rounding. Second, principal angle rotation measures whether the dominant singular subspace is moved. Third, normalized spectral shift measures how much the singular value spectrum changed. Fourth, update mask overlap asks whether visible updates landed on principal weights or low magnitude weights. This overview graphic is the visual map of the whole claim. SFT is dense and more principal aligned. Our LVR is sparse and strongly off principal. OPD lands between them, but closer to the RLVR side, and it quickly enters a low-dimensional channel during training.
Why do they call that region relaxed off principle?
Off principle means the update avoids the dominant pre-trained directions that would strongly reshape the model's existing representation. Relaxed means OPD is not as tightly constrained as our LVR. It moves more coordinates and rotates the geometry more, but it still preserves the pre-trained spectrum far more than SFT does.
What is the first concrete result behind that map?
For visible update sparsity, SFT leaves only 8.1% of weights unchanged. Our LVR leaves 77.2% unchanged, and OPD is in the middle at 51.6%. Across OPD variants, that sparsity stays roughly between 48.6 and 57.1%, so the result is not just one teacher-student pairing. The subspace and spectrum diagnostics point in the same direction. SFT rotates a representative dominant subspace by more than 10 degrees. OPD is around 1 degree. Our LVR is below half a degree. Spectral drift also steps down from SFT to OPD to our LVR, so OPD is selective but not frozen.
That tells us how much the model moves.
The update mask result is the clearest localization evidence. Global update density falls from 92.73% for SFT to 46.8% for OPD to 27.76% for LVR. Low magnitude overlap rises from 31.8% for SFT to 53.59% for OPD to 73.48% for LVR. So OPD moves away from principal weights and towards smaller magnitude regions, but less aggressively than our LVR.
What mechanism do they propose for why OPD lands there?
They adapt the 3-gate view used for our LVR. The first gate is an anchor that keeps the update budget bounded. The second gate is pre-trained model geometry. The third gate is numerical realization. Only updates large enough to survive bfloat 16 rounding become visible.
Where does OPD differ from our LVR inside that account?
The difference is the coefficient on each token gradient. Our LVR broadcasts one sequence level advantage across the response. OPD uses different token coefficients from teacher-student disagreement. That gives OPD denser descent directions inside the same anchored, geometry-steered family. That equation defines the gradient as a sum of token score directions. The important term is a sub-T. If every token shares the same reward coefficient, if the coefficient varies by token as in OPD, the update can cover a broader set of directions while still staying anchored.
The paper also talks about subspace locking. What is locked?
The locked object is the low-dimensional update channel. The authors track cumulative update matrices during training on measure stable rank, which counts the effective number of dominant singular directions carrying update energy. OPD stays in a narrow low-rank band. SFT expands its update subspace over time, while our LVR contracts toward a low-dimensional endpoint.
Low rank could still wander around. How do they show it is the same channel?
They compare each checkpoint stop 16 writes singular subspace with the final update subspace. OPD aligns with its final channel from the first measured checkpoint. SFT and LVR approach their final subspaces more gradually. That is why the paper says the OPD channel emerges early rather than being assembled late.
Is that channel only descriptive, or does it actually matter for learning?
They test that by forcing later training gradients into the early rank's 16 subspace. OPD remains essentially intact under that bottleneck. SFT degrades over the matched window. So for OPD, it is functionally sufficient for the learning that follows.
What controls whether the lock survives?
Runtime perturbations do not break it. Keeping only selected teacher-supervised tokens, even random 25% retention, preserves the OPD stable rank trajectory. Switching rollout generation off policy also leaves stable rank nearly matched, though the update norm changes modestly. Objective composition does change it. When they mix the OPD teach to correction signal with the RLVR reward signal, OPD dominant mixtures still look OPD-like. But once the OPD component becomes weak, the trajectory enters a distinct spectral regime. The sensitive factor is the objective signal, not merely which tokens or rollouts were sampled.
What should viewers take away from all those diagnostics?
The takeaway is that OPD is not just halfway between supervised fine-tuning and reward learning. It forms its own update geometry, relaxed off-principle localization, early subspace locking, and sensitivity to the teacher correction objective. That gives a concrete way to reason about why OPD can move more than RLVR while still preserving pre-grained structure better than SFT.
Does the paper claim this fully explains OPD optimization?
No, the authors are careful about scope. The diagnostics are computed from stored checkpoints, and the 3-data count is a mechanistic explanation consistent with the evidence, not a complete causal theory. They also note that the observed geometry may vary across other model families, modalities, and test distributions. That is the paper in one sentence. On policy, distillation improves reasoning through a distinctive, early geometry preserving update path, rather than by simply interpedaling between supervised fine-tuning and reward learning.